In New Zealand, introduced pests are a big problem for our native birds. Without human intervention, many species could go extinct. To prevent this, organisations like the Department of Conservation and Forest and Bird organise bird counts, where human volunteers count the number of birds they can see in a certain sample area. The results can be used to determine where a limited budget should be spent on traps and bait to save the most birds. I met with the Department of Conservation, and it turns out that bird counts can be quite imprecise. When the area being surveyed is very large, such as on a braided river, the volunteers can be up to 200 meters away from each other, and so there's every chance they could be missing birds. The birds can be hidden from the volunteers by trees, rocks, or even their own camouflage in the case of the banded dotterel. In some areas, the birds are too numerous and too hectic to be counted accurately. I had an opportunity to develop a technological solution for doctor use to count birds more precisely than volunteer bird counts. After reading about the success of drone-based hyperspectral imaging to map crops, diseases, and weeds, I decided to investigate whether the same technology could be used to monitor birds over long periods of time. Here's an example of an area that might need to be surveyed. To explain the concept, I've simplified the landscape a bit. Birds are in white. Here's how it could work. The drone is given a series of GPS coordinates, which it flies to in sequence, taking hyperspectral images along the way. The images are then combined into one larger image. Hyperspectral images don't just have 3 color channels, red, green, and blue. Instead, they have tens or hundreds of these color channels, which are called bands, and these cover much more of the electromagnetic spectrum than visible light. This means that hyperspectral images are 3-dimensional, with the 2 dimensions which are spatial and 1 spectral dimension, which is based on the frequency of light which it recorded. Every pixel in a hyperspectral image has a spectral signature, which is the amount of light it gives off for every band. To find out what a pixel is, we just have to compare its spectral signature to the ones that we already know. And to count birds, we just have to compare every pixel in the hyperspectral image to the spectral signature of a bird. Unfortunately, hyperspectral cameras are very expensive. A cheap one can be upwards of $5,000. This means I have gone for a proof of concept by replacing the filter in a webcam with an infrared-friendly one. Without a spectral camera, I can't take spectral signatures, but I'm hoping that infrared images will let me find birds. I wanted to have a Raspberry Pi attached to the drone, which could connect to a laptop on the ground. However, this is where I ran into some trouble. At first, I tried setting a static IP address for the Raspberry Pi by changing a Wi-Fi config file. However, every time I tried to change this file, the Raspberry Pi lost Wi-Fi functionality. Next, I tried to set up a hotspot on my laptop for the Raspberry Pi to connect to. Although it appeared to work, the Raspberry Pi did not receive an IP address, and so I could not make the devices connect to each other. Next, I tried to forcibly give the Raspberry Pi an IP address while I was connected to the laptop hotspot. This also seemed to be a success, except that neither FTP, SSH, or pinging either device from the other worked. Finally, I tried connecting both devices to a hotspot on my smartphone. This worked perfectly because both devices were able to connect and both got IP addresses. Also, FTP, SSH, and pinging worked for both machines. Using the Adafruit GPS module, I was able to get regular GPS updates of where the Raspberry Pi is. I then set up a server on the Raspberry Pi so that when my computer connected to it as a client, it would send regular GPS updates on a 1-second basis. I hoped that this GPS data could be used to make the laptop a visual aid for the drone pilot. It would let them know whether they're at the right point to take the next photo or not. This meant I wrote some Python code to take in coordinates and print them out on the screen for the pilot to use as a guide. I soldered together a battery, stuck everything onto the school's drone, and then took it down to a local field for a test flight. Considering that it got off the ground, it went better than expected. However, unfortunately, the GPS module did not record any data during the flight, and the pictures stopped working after about 12 images, which were being taken at 4-second intervals. It seems that the battery ran out after 48 seconds. These are the raw images which were captured by the camera. I did some color channel mixing so that the long jump pit would be brought out from the grass. Hopefully in future flights I'll be able to map the whole field. In the future I want to improve the connection between the Raspberry Pi and the laptop so that I can get GPS data going from the Raspberry Pi to the laptop during the flight. I also want the laptop to process this data and display it on the screen to act as a visual aid for the pilot. And then I want to be able to take the images that were captured and then make some sense of them using image processing. It's likely that I'm going to continue this project for much longer because it has such great potential. I'd like to acknowledge a few people for their help in my project, especially Mr. Crichton from my high school, Francis Del Prado, who has been regularly meeting with me to discuss the project and its progress, Terry Green and Andy Shooter from Department of Conservation, who have helped steer me in the right direction, and my parents, who have really helped with getting things done.